Welcome back, Astronomy 1020. We're watching Emily play with her kittens here, and that's kind of all the entertainment we need. Holy
Oh, a ferret!
Oh, it's a ferret. Where'd you get all those kittens, Emily?
We just adopted them a few days ago and brought them home.
Wow, so you're having a good time over there, huh?
Yeah.
It's going to be hard
It's
to pay
both my
attention.
ferrets.
My lecture. Oh my gosh, look at this. Wait, hold on. Were they all ferrets and I just thought they were kittens?
No, there's 2 kittens and 2 ferrets.
Oh my God, you got a damned menagerie over there. That's great.
Yeah.
Snake cat.
My house is like a farm.
Well, we're all going to have a hard time paying attention to our lecture today because it looks like that's going to be a lot of fun playing with those animals. Our lecture is going to be awesome today. I thought I would give you guys a break from stars because we've been doing stars for the last couple of weeks. And yeah, we did need that. We're going to talk about one of my favorite subjects in all of physics, which is special relativity, and maybe even a little bit of general relativity next time. Do you guys know anything about relativity? Have you heard about this before? This is Einstein's famous theory of space, time, and gravity that surpassed eventually Newton's theory of gravitation. And it's one of the things that Einstein is famous for, and it's just some cool, weird, freaky stuff. It also turns out that if we're going to understand the death of stars, we need to know about this subject. It just comes up in a lot of different places, and I enjoy it, so I thought you guys might too. Today, our lab is going to be kind of like a mathematical exercise, but it's an easy one. And what's very important about today's lab, it's on a famous paradox in relativity called the twin paradox. Now, I don't want to surprise you here. I'm going to give you guys an intense test question on the twin paradox. And that test question is going to be almost identical to the lab we do today. So today's lab is training for that question, okay? My board looks reasonably well framed here. Do I need anything else? Okay, let's try to get into it. First thing I want to do is hide the trolls, because we got to do that. As I was mentioning to Chris earlier, I did grade all the back homeworks and labs eventually, so that's good. Normally, I shut off the homework and lab after I grade it, but a couple of you that I knew had been in class and in lab failed to do the basic thing of submitting your assignment. So I tried to leave it open for a few of you. Please make sure that you took care of all that. And I'm thinking about Austin, who's somewhere in the background there. Let me just hide non-video participants. Okay. Okay, good. Now I can see the people that can see me. Let's talk about relativity and let's talk about why it's important. We'll start off with a little share screen here. And okay. Here's our lecture on relativity. Relativity turns out to be a theory about the motion of objects. You can think of it as surpassing Newton's laws of motion, but it's got some kind of cool and weird implications. One of them is that the 3 dimensions of space that we're familiar with, up, down, forward, back, side to side, those dimensions are connected to time in an intimate way. And after you learn about relativity, there is no longer such thing as independent space and independent time. There is a 4-dimensional space-time manifold. Yeah, that's why this stuff is fun to talk about. But hold on, we're going to take you there step by step so that those things sound less weird. But ultimately, that means relativity is a theory in 4 dimensions. And that can lead to some confusing thoughts and some furrowed eyebrows like Kaitlyn had just a moment ago. Sometimes it's nice to start off your relativity lecture by telling people about this legendary book from the early 1900s called Flatland, A Romance of Many Dimensions by Edwin Abbott. And it's a book that is kind of a thinly veiled critique of Victorian society. But the usefulness of the book is that it tells a hypothetical story about a three-dimensional sphere who makes friends with a two-dimensional square. And the sphere and the square become friends and ask each other about the world in which they inhabit. And they have some sort of funny realizations about it, what it means to consider a different number of dimensions than the one you live in. And see if you can follow me here really quickly. Let me lock myself. In the book, the sphere is a three-dimensional object, a ball, like you and I would be familiar with. And he makes friends with a being who lives in a two-dimensional world called Flatland. And this being is essentially just a square. He's a two-dimensional object. And the square and the sphere become friends. And the sphere says, well, what's it like in your universe? Like, how do people interact? He says, well, our society is based on polygons and the number of sides of your polygons. So if you're a triangle, you're kind of like a factory worker, like a worker bee. And if you're a square, maybe you're a civil servant. And then maybe if you're like a pentagon or a hexagon or something, then you might be a general or someone who's a little higher up in the societal class of our civilization. The highest member of their class is a polygon of infinite number of sides, which if you put your noodle on it, a polygon of infinite number of sides is actually a circle. And so a circle is a priest in their society. Now, this book has some retrogressive tendencies, and it's a thinly veiled critique of Victorian society. And women in this society, they were just lines, okay? And so the square is, I know. So the square is telling the sphere that it can be very confusing to figure out who you are talking to. Because if you're a square and you're interacting with different people, like here's a priest and here's a woman that you're talking to. If you live in two dimensions, you do not see the full two-dimensionality of the people you're talking to. What it looks like to you is she just looks like a line because you're seeing the line. But a priest who is a circle also looks like a line. They just look like a line that's a bit brighter in the center and then kind of trails off towards the side. So he said it can be difficult to figure out who you're talking to because everybody just kind of looks like a line with different shading. That's an important concept. You always see one less dimension that you live in. And that's true for you guys as well as it is for the square. Take rainbow ball for a second. Rainbow ball has different colors and different sides. But you guys, even though rainbow ball is 3D, 4 dimensions, Austin, maybe more, but at least 4. Rainbow ball might be a 3-dimensional object, but you guys only see a disk. You see a 2-dimensional projection of rainbow ball. For instance, you can see the pink side, but you cannot see the blue side simultaneously, right? A 4-dimensional being perhaps could. A 4-dimensional being would be able to see all sides of this at the same time, in the same way that we can see all sides of a square because we live in one more dimensions. Now, the ultimate drama of the book comes when the sphere decides that he's so fascinated by Flatland that he's going to travel through the 2-dimensional world. And he passes through Flatland so that the square can sort of see him and understand him. What do you think a sphere would look like to a set of 2-dimensional people? Well, as the sphere passes through the 2-dimensional surface, we take successive slices out of his sphereness, and this is what a sphere looks like to the 2-dimensional citizens of Flatland. First, there's a dot, and then a line that grows bigger and bigger and bigger until it reaches maximum radius. And then, as the sphere continues to pass through, something like that, right? Can you guys see it? That is what a sphere would look like to the 2-dimensional citizens of Flatland as successive slices of himself pass through. I wonder what it would be like for us three-dimensional beings. If a four-dimensional sphere, a so-called, thank you, hypersphere.
Oh my God, am I not on mute?
Oh, you're on mute now. That's okay. I didn't hear you say anything crazy, so. What would it be like for us if a four-dimensional sphere, a hypersphere, could pass through our three-dimensional world? What if we tried to transpose Flatland into our three-dimensionalness? Can anyone imagine what that would look like? Maybe I shouldn't have given you guys the flat. Fuck, it's weird. Okay. Actually, well, it would definitely look weird. But I was hoping you guys could sort of bend your minds with me here.
I'm lost. Yeah, no, I am lost. I don't know.
Did I lose you with this? Okay, well, maybe I'll just tell you and you can think about it. Ours would be the equivalent of this. No, it is not possible for us to see the front and back of the hypersphere. That's one dimension above us. Just as it's not possible for the square to see the front and back of the circle at the same time. For us, a four-dimensional sphere would look like a set of spheres that grows and shrinks. It would start off as a dot, and then slowly the bubble would grow to greater and greater sizes, reaching some maximum spherical extent, and then it would shrink back down into nothingness. That's what a 4D sphere, a hypersphere, would look like if it passed in slices through our three-dimensional world. Anyways, that was just a little get your noodle cooking kind of thing. Maybe we'll start off slower because you guys clearly didn't like that and couldn't handle that. Let's start by talking about what a dimension is. Maybe the problem is that you guys just don't know some simple basic things that we got to talk about. Like, what's the difference between 2D, 3D, and 4D, okay? So let's start with a dimension, the concept. A meter stick is a pretty good example of a one-dimensional structure. It's essentially just a number line. And when I make this number line, I draw the line and I have to decide where the origin or the 0 point is. Physics is often about measuring the positions and the velocities of things. So you have to decide what you're going to measure with respect to. So I'll pick my origin to be here, 0 meters or something. And I will tick off some kind of grid. I basically have to choose my units of how I'm going to measure distances. And I will choose, do you guys know what a decameter is? Do you know about King Henry's dog drinks chocolate milk? King Henry's dog drinks chocolate milk. This is how we teach students the metric system. Kilo, hecta, deca, deci, centi, and milli. Anyone ever heard of King Henry's dog drinks chocolate milk? Christopher says no. Okay, this is 10 to the 3, 10 to the power of 2, 10 to the power of 1, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. This is where millimeters come from, centimeters, decimeters, decameters, hectometers, and kilo. Usually we don't use hecta and deca too often. But today I'm going
to have to put deca and deci right next to each other. That's just rude.
That is rude. Yeah, I agree. But hey, it's got to do with Latin, so don't blame me. We're going to use decameters. So this is every decimeters. That's what we're using right now. 1/10 of a meter. When I tick off these numbers, so this is 1 decameter, 2 decameters, 3, 4, 5. I have constructed something that in relativity we define as a metric. A metric is when you take a dimension, like a one-dimensional number line, and you say, I am going to grid that metric out in these units of decameters. This is 1 decameter from the origin, 2 decameters. That is a one-dimensional construction. If you wish to go, oh, by the way, in 1D, of course, you can measure forward or back. right or left. It's very simple. Oftentimes, we can approximate motion as one-dimensional, right? If I tell you I drove from Providence downtown to CCRI at 90 miles an hour in my van, we kind of assume that I'm driving in a straight line, even though in reality, the road probably has some twists and turns along the way. Sometimes the twists and turns are less important than going from point A to point B. If I wish to go from 1D to 2 dimensions, I must add another number line, but this number line must be perpendicular to the original one so that they are completely independent. So here, I draw a second number line, my y-axis, and I can also grid out decameters for this as well. So 1, 2, 3, 4, 5, 6, so forth and so on. This is now a two-dimensional construction, right? Because I can find a coordinate 1, 2, and I can describe its motion in both forward, back, and up and down, or however you want to think about it. This has a two-dimensional construction because there are two directions of motion. And likewise, I can take a third number line that's perpendicular to all three of these, and I can make a z-axis, and I can go from 2D into 3D. It seems to me that every time we make another dimension, we have to add another number line that is perpendicular to all of the number lines that come before it. For instance, this number line here is supposed to be sort of in and out of the plane of the board, completely independent of these two number lines. And I can find a coordinate there, if I wish, in 3 dimensions. It will have 3 coordinates, x, y, and z. I suppose if I wanted to make a 4-dimensional construction, I would just need a 4th meter stick, and I would need that to simultaneously be perpendicular to all of the other dimensions. It would have to be perpendicular to x and y and z. It turns out that that's hard for us to imagine because we are inherently 3-dimensional creatures. We cannot construct 3 meter sticks, x, y, and z, and take a 4th one and make it perpendicular because we are within a 3-dimensional space. But that does not mean that you can't imagine it. That does not mean it's not mathematically valid. And it turns out that that's a better description of our universe than the 3 dimensions that you're familiar with. Okay, so for us to be able to explain how we eventually arrived at these conclusions, you have to go back and understand some basic concepts in physics. And now we're going to give you a little foreground training in relativity. Foreground training about how we measure motion using these coordinate systems, okay? So hang on to your hats. The first concept that I'd like to develop with you is a concept, let's see if we can find it here, called an inertial reference frame. And maybe we should even just talk about what a reference frame is. A reference frame is some kind of a coordinate system that you use to measure the motions of objects. This, for instance, is a 2-dimensional reference frame, and I can measure an object's position as it moves around the chessboard, x, y, okay? Let's sort of construct a reference frame. Let's imagine we were going to watch a skateboard punk ride his skateboard across the classroom, okay? So what we'll do is we'll construct a little frame of reference. We'll have a y-axis, and we'll have a z, or an x-axis, excuse me. So this, for instance, could be a classroom, and we're going to put a dude, an observer dude, at the origin of the classroom. We've decided that the origin of the classroom would be, I don't know, the left-hand corner. And that's where our observer is going to watch a skateboard team ride around the classroom. So we'll make ourselves a skateboard. Actually, let me put him a little further out That's going to be helpful here. Okay. And we're gonna play a little game here where an observer called A is going to measure the position and the velocity of an observer on a skateboard called B. The first thing I would like to point out is that observer A in the left-hand side of the classroom constitutes one frame of reference. He has an x-axis with 0 on the left, and he can measure the position of the skateboard in meters or in decameters as he rolls across the classroom. B on his skateboard also constitutes a second frame of reference. If I wanted to, I could put a little flagpole on B's skateboard, and even though B is moving, his moving skateboard sort of constitutes a second reference frame with which he can watch the universe evolve. He's riding along on a flat board. The board could constitute 0 meters for him. He's sort of at the origin of his own little skateboard universe. And this is a second reference frame. This is an important concept. Different observers at different locations are going to have different frames of reference. A measures with respect to himself. B measures with respect to his self, okay? In physics, there is a concept called the inertial reference frame, and this is the first vocabulary term that you need to learn today. So introducing the inertial reference frame. An inertial reference frame is a coordinate system that moves at a constant velocity. And I'm underlining constant velocity because that's the key idea. Let's say that observer B travels on a skateboard with a velocity of 5 meters per second. Hey, students, let's go back to one of our earlier lectures. Who out there remembers the difference between a speed and a velocity? This is a talk that we had at one point.
Is it direction?
That's right. A velocity has direction as well as magnitude of speed. Could we make this skateboard a velocity instead of a speed? Would that be possible? Does this skateboard have direction?
I mean, it does, right? It's going right.
It's going to the right. So let's make it a velocity, a proper velocity, by giving it a speed, 5 meters per second, and a direction. And I want to show you how we write directions in mathematics. I'm going to use an R for going to the right, and I'm going to put a little hat over it. This is some sort of advanced math notation. R hat means the skateboard travels 5 meters per second to the right. And the fact that I put the hat on there means this is not a variable like V. It is not a unit like meters per second, but this is a thing that specifies direction. This means the skateboard has a velocity of 5 meters per second to the right, okay? Let's start by asking a couple of simple questions to make sure you understand. Does B constitute an inertial reference frame? Yes or no? Is anyone even listening to me? I'm starting to have doubts.
What was the question again? I'm sorry.
There we go. The question is, does B constitute an inertial reference frame? Devin says yes.
Wouldn't it depend on if the skateboard will stop or infinitely keep moving?
All you know right now is that the skateboard is traveling 5 meters per second to the right. Forget about what happens in the future. At this moment,
Okay, so yes.
yes, because the skateboard travels at a constant velocity. Does A's reference frame constitute an inertial reference frame?
No,
Why not?
it's not moving.
False. Devin says yes. And Devin would be correct because a velocity of 0 meters per second is also a constant velocity. And you needed to be kind of explained that because for some people that was not going to be obvious. An inertial reference frame is any coordinate system that travels either at a constant velocity to the right, a constant velocity to the left, or a velocity of 0 is also a constant by mathematics. Therefore, both A and B constitute inertial reference frames. An inertial reference frame is any reference frame that has a constant or 0 velocity. You've just learned an important thing. Okay, now we're going to take you into the second step of logic here. Let's take a red tennis ball, like moon ball here. And suppose we give the moon ball to observer B, and we ask him to throw the ball as he's riding the skateboard across the classroom. What would the description of motion look like for observer A versus observer B? Observer B takes the red moon ball and throws the moon ball 2 meters per second to the right. According to observer B, that ball is traveling at a velocity of 2 meters per second. What will the velocity of the ball be according to observer A? I'm going to get my stool handy here because I have a feeling there's going to be some long pauses today. Okay, Devin's suggesting something. Devin suggested 7 meters per second. How'd you do that, Devin? How'd you figure out this complex stuff that eludes our fellow students? Okay, so Devin says, I added the two velocities together because the dude on the board is traveling at 5 meters per second, and he sees the ball at 2 meters per second, so I added 5 plus 2, and I got 7. Congratulations, Devin. You just did some math, and you did a very special thing in physics. Believe it or not, what Devin just, I hope you can all see what Devin did, because if you cannot, the rest of this is going to get real nutty. Okay. Devin did a thing that has a name in physics. Oh, look at that little kitten. Okay, this is gonna, if it's kittens versus relativity, I'm not sure who's gonna win, okay? What Devin just did there is a concept in physics called the Galilean transformation of velocities. It's another key vocabulary term that you need today. It was invented or described first by Galileo. The Galilean transformation of velocities. The Galilean transformation of velocities could be symbolically written like this. The velocity of the ball, according to observer A, is the velocity of the skateboard B plus the velocity of the ball. Where these are vector quantities, they have direction as well as magnitude. In other words, the speed of the ball according to A will be the speed of the skateboard plus the speed of the ball. Okay, class. Let's see if someone besides Kevin can do this. Kevin got the last correct answer. We'll give him a chance if you can't do it, but I'm just curious to see if anyone has grown from this experience. Let's say now I have a different scenario. Oh, by the way, just to write out what happened here, in the first case, the velocity of A was 5 meters per second to the right plus 2 meters per second to the right equals 7 meters per second to the right. That's what just happens there, okay? Now we're going to try a second scenario, okay? Now we're going to take the tennis ball, and in the second scenario, observer B is going to throw the tennis ball 2 meters per second to the left. What will the velocity of the ball be according to observer A? Someone besides Kevin try this.
3.
3 meters per second, but you need a direction, Kaitlyn. Which direction?
Left.
Gotcha. It's not to the left. It's 3 meters per second to the right. Haha. Does anyone understand why it's to the right and not to the left? I was hoping I'd trick someone, and I tricked you, Kaitlyn.
Oh, is it because the direction doesn't change? It's not strong enough to change the direction?
I get that's sort of one way to say it. According to B, the ball moves to the left, but according to A, the ball was already traveling. Oh, did I say Kevin or Dev? I think I said Devin, Kevin. There's too many Kevins and Devins floating around in the background. I can't tell you all apart. Okay, look, in any case, it's not important. The skateboard is traveling faster to the right than it is to the left. You agree with that, Kaitlyn, right? So let's just look at it from an algebraic point of view, okay? In the second scenario, the velocity according to A is 5 meters per second to the right. And I want you to carefully watch how I do this. Plus 2 meters per second to the left. Okay, it looks like I'm adding them, but now I'm going to make a substitution that's going to make you laugh. The direction of right is the negative direction of left. Isn't that true? Isn't it true that right is negative from left? I can substitute negative r in for L to get 5 meters per second to the right minus 2 meters per second to the right equals 3 meters per second to the right. Did you see how I pulled some tricky Ricky stuff on you there? But yes, Kaitlyn, there's an easier way to do this, which is to think your way through it. The skateboard is moving faster to the right than the ball is being thrown to the left. So even though B sees the ball moving to the left, A sees the ball being carried forward to the right because you've just subtracted a little bit from this velocity. Please tell me someone understands what I'm saying. Okay, thank you. That's great. Hey, can I point something out before shit gets real weird here? Can we all agree that in the second scenario here, observer A and observer B do not agree on the same direction of motion for the ball? Isn't that true? They have different descriptions of what's happening. A says the ball is moving to the right. B says the ball is moving to the left. Is that okay for two observers to have different descriptions of motion? That's okay. It's okay if two people do not agree on what's happening. This is the normal world of physics that we've all grown up with, the one that we expect to transpire when people throw balls when they're rolling on skateboards. It is normal. And what makes it normal is we assume that velocities just add and subtract in logical ways. Galileo was the first person to describe this. So this concept, which is supposed to be common sense in a way, although we just discovered it's not always common sense, But this concept has a name called the Galilean transformation of velocities. It turns out that Albert Einstein discovered that it's false. It's actually not true. And that's the real buggy thing about relativity, about special relativity, that we're going to discover today. Okay, I need to erase this, so let me make sure everyone's got it copied down. There's a couple of different puzzle pieces I need to give you here before we can move forward. I want to talk about something that's not necessarily related to Einstein. It's just a different concept or a principle. And it's known as, sometimes I think they call it the relativity principle. This actually predates Einstein, and it's important to have this in the back of your head as we go forward. I'm going to write it down, and then I'm going to try to explain it to you. Any observer in an inertial reference frame, any observer, whether they're observer A in the classroom or observer B on the skateboard, can always argue that they are, and I'm going to put this in quotes because it's a little ambiguous, at rest. And let's say can always successfully argue, provided I spelt that right. Any observer in an inertial reference frame can always successfully argue that they are at rest. And let me give you an example of why this is true. Imagine that instead of a skateboard, we instead put observer B into a very smoothly running boxcar on a train, okay? So let's construct ourselves a boxcar. Let's make it, I don't know, 20 centimeters long on both sides. And the reason I choose a boxcar is because a boxcar by its nature does not have any windows, so you can't see out of it. And I want you to imagine that I grease up the tracks with some very slick oil so that there's hardly any friction between the wheels and the train tracks, so that you can't really hear the clickety-clackety of the train. And then we put a chair inside and have observer B sort of sit in the chair.
Math is so easy, so I'd better have the same Sunday as we just did. That's my goal.
Hey, what's up, Chatterbox Cafe? Are you participating in the class, or are you just talking to your friend? Does someone need to get involuntarily muted? Oh, I can't find you. Okay, never mind. I gotta hide those trolls again. I'm just teasing you. Okay. Let's imagine that we put an observer inside the boxcar. We black out all the windows and we cover it with sound canceling. That's okay, Cam. That's not a big deal. We cover the train car in sound canceling foam. Even if this train car is moving at a very rapid velocity, even if it's traveling at 50 meters per second, there's honestly no way for the observer inside the train car to know that they are in motion. In fact, if you think about it, there's no physics experiments that they can perform that would tell them that they're in motion, because here's the thing. Motion at constant velocities, in a way, is the same thing as being at rest. When you measure velocities, you measure your motion with respect to other things. What if we stripped away the train tracks? What if we stripped away planet Earth and the other stars? If this train car was traveling through space at a constant velocity, there's nothing you can do to tell whether you're actually in motion or not. For instance, here's one version of an physics experiment. I could take rainbow ball here, and I could put rainbow ball on the floor of the train car. And we would discover that rainbow ball would sit there perfectly still as the train car rolled forward. Now, if there was an acceleration, if the car starts to speed up or slow down, then the ball would actually roll back and forth the way sometimes your groceries slide around in the car when you hit the brakes. But if you're traveling at a very constant velocity, this ball will be completely motionless in the same way that it would if you were sitting at rest inside of a train station. It turns out that there's no experiment you can conduct inside of a train car. If the velocity is perfectly constant, there's nothing you can do. If you can't look out the window to see what's going on, you cannot really tell if you're at rest or in motion. That becomes particularly true when you're in outer space, when you don't see any trees or mountains flying past you as you drive down the road. In fact, there's this kid, this like teenager, and he made a video. When he was in high school, he made a video about relativity, and it became such a hit that he submitted it to some contest, and he won a free tuition or free scholarship for 4 years of college and like $100,000. And he just made this video in his mom's backyard with a little handheld camera. It's kind of a cool thing, but he actually addressed this point in a kind of very convincing way. So much so that I think it's probably worth sharing with you guys, even though it'll take a second, because I really want to drive this point home before we go forward. A lot of things I do are going to depend upon you really believing what I just said. So kid wins, let's see, relativity video scholarship. Yeah. So this kid, now I'm not going to show you the whole thing, and YouTube's probably going to get annoyed with me here because I'm showing a YouTube within a YouTube, but I don't care. I want you guys to see just 2 or 3 seconds of this here. So first I need to know if you guys, can you hear the sound?
To be complicated or hard to understand.
Can you guys hear the sound of this?
I bet we could formulate it ourselves.
Yeah, we can.
Two postulates.
Okay. He's going to go through the two postulates of special relativity, but we're going to get to those in a moment. I just want you to see the 2 minutes, not even the 2 minutes, the 30 seconds where he tries to explain this relativity principle, because it's kind of funny here. So, okay. So let's just go and we're going to watch 30 seconds of this video because he's going to help make my point in a very dramatic way. Let me make sure my volume is up first. Hold on a second. Okay. So check this out.
Just sit in a chair.
Hold on a second.
Pop easy to prove. To be constant or slowing down. But why does the speed have to be constant? Well, that's easy to prove. Just sit in a chair, grab a bowl of popcorn, place it in front of you, sit back, and watch how the laws of physics behave. Nothing's happening. Now let's do the same thing in a car with the windows blacked out. What if the driver decides to change the speed of the car drastically by stopping all of a sudden? All of a sudden, the laws of physics seem to act a bit differently.
Okay, look, so that kid was really great. Like, he made this like little silly YouTube video. He won himself a free scholarship to college, and he showed us that these things that seem so abstract to us, these relativity principles, can be very easily understood by stuff in our everyday world. Very clever. So let's remember this. If an observer is traveling, even at a very rapid velocity, as long as its inertial reference frame, as long as the velocity is constant, in a weird way, this observer could argue that their train car was at rest and that it was the entire set of train tracks, and indeed the planet Earth that was traveling away from him instead. I'm going to drive this point home with one more goofy video. In the 80s, there was this really terrible comedy movie with Val Kilmer called Top Secret. And this goes back to the days when Germany was still occupied by Soviet Russia, and East Germany and West Germany were divided in half. And Western cultural things like rock and roll and blue jeans could not be imported into East Germany. So in this movie called Top Secret, train gag, a very young Val Kilmer is an American rock and roller who's going to go to East Berlin and show these Stasis about rock and roll and democracy and all this stuff. Now, it's interesting that this train gag is sort of taking place here in East Berlin. The writers of this movie were certainly conscious of the fact that Einstein was a citizen of Germany. The whole thing is maybe 20 seconds long, but I think it's worth watching. The movie is definitely not worth watching. It's pretty bad, but just humor me for a second and take a look at this here, okay? So at the beginning of this clip here, he's on a train and he's about to leave a station, and the Germans are saying, "Show me your papers," and all that stuff. Anyways, as you can see, it's a very silly movie, but that is an ingenious clip there that I wanted you guys to see so that you'll have that in mind when we talk about inertial reference frames. Any observer who travels at a constant velocity could always be at rest, and motion is relative. It depends. What you really notice is you notice accelerations. When you speed up, when you slow down, you can feel forces. When you turn the corner on an exit ramp, you can feel the car pressing into your side. You can feel those forces. When a velocity is constant, there are no forces involved. And without any forces, you can't measure and determine if you're in motion. It turns out that when you approach the speed of light, things get a little buggy in nature. And let's talk about why. The speed of light turns out to be a special velocity in physics. Do you guys remember what the speed of light is, the value of it?
286,000 miles per second.
Ooh, did someone just use miles? Oh, where's the soap so I can wash that bad taste out of my mouth? That is disgusting. Don't ever talk to me like that. The speed of light in some sort of more civilized units, like for instance, some metric units, okay? The speed of light, which we give the letter c, up to now, you've used it as 3 times 10 to the 8 meters per second, okay? However, meters aren't always the best unit to use when we're talking about the motions of stars. So my personal preference is to use for relativity calculations 300,000 kilometers per second. That's kind of nice because if we use the rules from our class, we don't use scientific notation until we get to 1,000,000. Just a little bit easier and more comfortable to look at, okay? So for our relativity calculations, we're going to try to go to this number. Do you guys have any idea how one measures the speed of light? I mean, it's pretty fast, right? It's not like you can. Where's my laser pointer? It's not like you can just sort of click on this laser and poop. I mean, it seems to be instantaneous. There's a long history behind attempting to measure the speed of light. And although you wouldn't believe it, the first person who ever tried to do this was actually Galileo himself. And Galileo attempted to measure the speed of light by shining a flashlight from one mountain to another with his friend, but he failed the experiment because the friend basically measured the velocity as being instantaneous. As soon as he opened the shutter, the friend saw it. But Galileo didn't give up. He believed that it might be possible to measure the speed of light. It turns out that the modern way that we measure the speed of light, let's go to my slideshow here, is with a device called the Michelson-Morley interferometer. And this might end up being like a little much for you guys, but let's just talk about it. It's kind of cool to learn about famous experiments in physics. You guys might remember that at some point I showed you what's called a diffraction pattern, where I took a laser and I shined it through a couple of thin slits, and you guys saw the laser beam scatter out into a whole bunch of dots. We actually use the diffraction of light to measure the speed of light. We take a laser beam and we fire it through something called a half-silvered mirror. And a half-silvered mirror will transmit 50% of the laser light and will reflect 50% of the laser light. And basically, we split the laser light into two half beams. One beam, which travels to a fixed mirror, bounces off, reflects, and hits a screen. The other laser path bounces off a movable mirror and reflects off the movable mirror and transmits through the half-silvered mirror onto the screen. So both lasers are kind of sent to the left and to the right here, or let's say along the x-axis and the y-axis, and then they are both brought back together. Now the trick is the movable mirror is on a very, very finely articulated screw that can move the mirror back by small increments in distance. And by changing the distance that the light travels by a small number of wavelengths, you can create an interference pattern on this screen. And by measuring the distance between the bright fringes and the dark fringes, you can calculate the difference in the path that the laser took, and therefore you can calculate the velocity. Because this instrument has incredible sophistication, today we know the measurement for the speed of light to a greater precision than almost any other constant in the entire universe. In fact, the speed of light is known to such an incredible precision that today we base the definition of a meter, and we even base the definition of a second off of the measurement of the speed of light. We are more confident in our ability to measure the speed of light than we are even confident in our ability to measure time or our ability to measure lengths. And it's kind of wild. Now, in the early 1900s, people began to notice that there was a problem with measuring the speed of light relative to other objects. And one of these experiments, well, I've got to walk you through a couple of different concepts here. So let's talk about the nature of light and what it is. As you learned in a previous lecture, light is a time-varying electromagnetic wave. That means it's an electromagnetic wave that has a magnetic field and an electric field, and they wiggle and they travel through space. Light is similar to other waves, as you learned before, like a mechanical wave on a string, and that a light has a wavelength, it has a frequency, it has an energy associated with it. One thing that light does not have that's a little awkward is most waves have a medium through which they travel. For instance, if I make some waves on a spring, if I were to take a spring and make some waves here, the medium of the wave is the spring itself, right? On a mechanical wave, the string is the medium of the wave. In an ocean wave, the medium of the wave is water. What about a sound wave? What is the medium of a sound wave? Air, says Devin. That's right. My vocal cords are vibrating compressions of air that travel through my bedroom into this speaker here and eventually into your ears. Air is the medium through which sound waves travel. 19th century physicists got a little concerned that light was a wave phenomenon that did not have a medium. Because if you think about it, every day, light makes a journey from the sun to the earth in 8 minutes. and light is a wave that is traveling through the vacuum of space. 19th century scientists could not understand how a wave could propagate through empty space and get from the sun to Earth, and they became very concerned about it. So concerned, in fact, that they decided that empty space might not be empty after all, but might be an invisible medium known as the luminiferous ether or the superluminiferous ether. This is basically a fancy way of saying the vacuum of space is somehow a medium through which light can travel. And they attempted to set out and measure the speed of light relative to the luminiferous ether. They performed a famous experiment that you need to know about called the Michelson-Morley Experiment. Let's see if we can't take you through that. The Michelson-Morley Experiment was an attempt to measure the speed of light relative to the background vacuum of space. And it proceeded in a kind of goofy way. First, we have the sun. And second, we have the Earth. And the Earth is traveling around the sun in an almost perfect circle. The velocity of Earth around the sun turns out to be pretty close to 30 kilometers per second. Pardon me. The idea behind the Michelson-Morley experiment is that they were going to fire a laser beam in two different directions to try to measure the speed of the laser relative to the superluminiferous ether. The first laser beam they were going to shine directly along a line between Earth and the sun so that none of the Earth's velocity would carry the laser with it. So the first laser beam, they would shine in this direction. And for the green laser, of course, the velocity that they expected to get was simply c, the speed of light, 300,000 kilometers per second. And that's because since the Earth's instantaneous velocity is in this direction, sort of tangent to the circle, no component of the Earth's motion will add or subtract from the beam. The beam is perpendicular to the direction of Earth and therefore should have the standard velocity of 300,000 kilometers per second. However, the second laser beam they attempted to shine in the direction of Earth. So let's say they took a blue laser beam, just for argument's sake, and they shine the blue laser beam in this direction. What would you guys expect to be the new velocity of the laser beam if we fired it in the direction of Earth? According to the Galilean transformation of velocities. Are you guys lost here? Did I use too many fancy vocab words? Have I challenged you too much today? Do we not want to learn about relativity? I mean, I could tell you more about my show. I don't know what you guys are interested in. No, look, this is very simple. What you guys just learned about the Galilean transformation of velocities. You understood that. What will be the velocity of the blue laser beam if I shine it in the fucking direction of Earth? Use your fucking addition powers. I know you can do this. Thank you, Cameron. Cameron understands me. He says, according to the Galilean transformation of velocities, it will be the speed of light plus the velocity of Earth, which is 30 kilometers per second, for a net total of 330 kilometers per second. The velocity of light plus the velocity of Earth. This is a measurement precision of 1 part in 10 to the 5. That is doable by a sophisticated modern physics laboratory. In fact, they performed this. It was somewhere in the Midwest. I can't remember if it was the University of Colorado or whatever. But here's a picture from the experimental apparatus of the Michelson-Morley experiment. And look how crazy this is. Basically, they have their Michelson-Morley interferometer with the half-silvered mirrors set up on a massive block of granite because they were worried that vibrations from trucks and things outside would be capable of throwing off the precision of the experiment. And then they floated the block of granite on a, what someone asked me what year. This was like 1887 or something like that. Late 1880s, 1890. They floated the block of granite on a pool of liquid mercury so that as they fired the laser, they could rotate it in a 360-degree circle. This is ingenious. The idea is that 50% of the time the laser would fire in the direction of Earth, and 50% of the time the laser would fire perpendicular to Earth. And they would be able to measure a small change in the velocity. Guess what they discovered when they performed the experiment? The experiment was what you kids would call a fail, okay? An epic fail, because the speed of light, no matter which direction the laser was fired in, was 300,000 kilometers per second always. It's as if the velocity of Earth had no effect on the laser whatsoever. Modern physicists could not understand this result. They were flummoxed. It was as if the laws of physics had broken right in front of their eyes and there was nothing they could do about it. One of the most basic, simple ideas that 1 + 2 = 3, that velocities should add, had stopped working. Well, about 20 years later, Albert Einstein came along and as a young man proposed a solution to the dilemma. There's a whole cool backstory about it that I kind of don't have time to get into, about him working in a patent office and submitting this letter to a newspaper, but I'll leave that up to your history books. Albert Einstein came up with these so-called postulates of special relativity, where he decided to turn physics on his head and in a sense suggested that maybe the results they got in that experiment weren't so weird after all. Maybe that was the way that nature was supposed to work. And in 1905, he proposed the two postulates of special relativity in a way to deal with the problem of this superluminiferous ether. So I'm going to erase here and I'm going to write those postulates down. Yes, you do have to memorize them. They're important to me. Okay. So Einstein's two postulates of what is now known as special relativity. Sometimes we call it SR for short. I'm going to say a couple of things here. First of all, do you guys, you probably don't know what a postulate is, right? Sorry, I'm just looking for a slide here. Where are you guys? I lost you. A postulate in mathematics means I can't prove this is true from the beginning. I'm going to assert that it's true. You will agree to believe me, and then the two of us will consider what the consequences are, and we'll see if we like them. I think Euclid had some postulates in his initial geometry lesson, and one of them was that between 2 points, there is exactly one straight line. That was a postulate that he proposed that later on people thought about it and said, you know what, that makes good sense to me. I think I believe in that. Turns out to also be false, but whatever. Okay, so Einstein's two postulates of special relativity go like this. The first one says the laws of physics stay the same in all inertial reference frames. And this basically dealt with the fact that he didn't want the laws of electromagnetism or the laws of gravity to change for one observer versus another if they were traveling at rapid velocities to each other. This was not considered a controversial postulate. People kind of just assumed this was true from the beginning, but he had to make a point to describe it. One of the reasons was he was concerned that if you could travel at the speed of light next to a photon, the photon's frequency would go to zero and the photon would lose all of its energy. It's kind of an abstract thing. But in any case, all he's saying here is if you're an observer moving in a skateboard or a rocket ship or a train car, gravity, electromagnetism, the strong and weak nuclear forces, they should behave identical for both observers. It was the second postulate that was the very controversial one. The second postulate states that the speed of light, c, is a constant for all observers. In a way, it's saying that there is no Galilean transformation of velocities. Although it's not obvious at this point, this is going to turn out to imply that the speed of light is actually the maximum speed allowed in nature, although we will have to prove that later. It's the maximum speed in nature. If you assume that the speed of light is a constant for all observers, some very wacky and buggy things start to take place. And I need to tell you about one of them because we're going to be using them in our lab today. One of the effects of special relativity, or the consequences, is a wacky result called time dilation. Okay? Time dilation asserts that clocks will run at different speeds when observers travel at different velocities with respect to each other. And I'm going to walk you through this as best I can. Can I erase here? You hate that. All right. Wait, no, you're still writing, Christopher? Christopher, could you share your freaking video with me so I can, it's really hard for me to fucking figure out what's going on with you guys when you're trolling me. If you need more time, that's fine, but you can give me a thumbs up. All right. Are you good? No, okay. By the way, Christopher, did I send you an email or did I get distracted? Christopher, one of your things was not submitted. Do you know that? Could you fix that for me, please? Jeez, guys. All right, can I erase?
Yeah.
Okay.
But also, I hate that time dilation shit.
Well, hold on.
Annoying.
Why don't you let me prove it to you? Do you hate things that are true? Do you hate the sunlight because it warms your face? Do you hate the stars?
Confusing.
What?
It's confusing.
It's confusing at first because you're unfamiliar to it. You know, chess is confusing the first time you learn how to play chess, and then you realize it's a beautiful and elegant game that's fun to do on Thanksgiving. Your favorite video game is confusing the first time you play it, and then you spend 500 hours doing it because it's so much fun, okay? Confusing things are fun. You have to unconfuse yourself. That's the game. Let's talk about something called the consequences of special relativity. Now remember, when Einstein proposed these two postulates, other intellectuals of the day read them and thought, I don't know if I buy that. That sounds a little crazy, Mr. Einstein. And then they began calculating through what this would mean for physics, and one by one, all of the predictions turned out to be true. Here's one of them that's really messed up. It's known as time dilation. And I'm going to attempt to prove it to you because Christopher hates that and so do other people. Time dilation states the following consequence, okay? It states that time runs, or actually, I'm going to write this in a different way. Moving clocks run slow for an observer who travels at a high percentage of the speed of light. And the percentage above which you start to notice moving clocks run slow is usually when the velocity is greater than or equal to about 20% the speed of light. This is what we call the relativistic regime, when things like time dilation start becoming apparent. Okay, for the setup here, to make sure I prove this proper, this is going to involve a teensy bit of math. I'm going to need to know that you guys are familiar with two formulas. The first formula, to prove this, you need the formula distance equals rate times time. Now, I had to do distance equals rate times time in high school. If you didn't, then someone along the way has failed you, and you should consider, suing them or firing your local political representative. Distance equals rate times time is a classic, okay? The other thing that you're going to need is the Pythagorean theorem. I'd like to imagine that someone out there in the studio audience knows what the Pythagorean theorem is. All right, Kaitlyn.
A squared plus b squared equals c squared.
Fine. And what
Nah, I never heard of it.
Never heard of this?
He steals the show.
Wait.
I'm just kidding. I'm just kidding.
All right. Okay. Well, I just don't know what sometimes I say like little simple things that you guys like, you're like, what the fuck is a proton? And you guys look at me crazy. So I don't even know what you guys know anymore. I assume you know nothing. Okay.
Wait, what is a proton?
Actually, that's kind of a good question. It's a combination of two up quarks and one down quark. How's that work for you? Okay. Positively charged defines an atom. I mean, that's what I would say if you asked me that question. I would have a whole bunch of bullet points to rattle off at you. I don't just go, well, sometimes I do, but not in that case. Okay, so remember that the Pythagorean theorem, A and B are the legs of your triangle. Cameron, we'll get to that in a second. C is the hypotenuse of the triangle. Now, I don't want to use the Pythagorean theorem the way that you learned it in high school, because obviously C is what we've been using for the speed of light, and that's going to get very, very confusing. Guys, we're going to get to your questions. We're going to get to those. I am going to rewrite the Pythagorean theorem as x squared plus y squared equals s squared. It's just a change of variables so I don't get confused with C. So in the triangle, x is going to be the x-axis, y will be the y-axis, and s will be the hypotenuse of your triangle. Can everyone deal with that? That's manageable, right? Whatever. Okay. You need these two formulas. Okay. Let's go ahead. I'm going to need to erase this here because I'm going to need a lot of work. Has everyone copied down this statement? All right. Okay, to do this, let's reconstruct our train car experiment. Let's put one observer on a train station watching a train car roll away. We'll call this observer observer A. And this is the observer who we initially think of as being at rest, okay? I'm going to call this observer A. And observer A is going to watch an experiment performed by observer B in a boxcar, in a train car. And I'm going to draw the train car at 2 different times, okay? Let me see if I can make it the same length, because that will help us. That will help our cause here. So this will be the boxcar at the first position. That's 20 centimeters long. And this will be the boxcar at the second position. I normally have a much bigger board to do this, so it's going to be a little dicey. And you guys might want to draw along with me here, because if you want to understand this, you have to understand this picture. And now I'm going to draw the top of the boxcar. Let's put a second observer, observer B, at the edge of the boxcar, okay? And I'm going to use blue for observer B to stay color coordinated here. Let's do this again. The reason why I'm drawing 2 boxcars, students, is because this boxcar is going to be rolling forward. Let's put some wheels on a very smooth track. And we're going to give this boxcar a velocity of, oh, I don't know, 80% the speed of light, which is clearly in the relativistic regime. Not times Christopher Leonard plus x squared plus y squared equals s squared. Get rid of your times and turn it into a plus. Okay. Now, at the start of the experiment, we are going to place a laser, a red laser, at the bottom of the boxcar right in front of B. And this red laser is simply going to fire a single red laser pulse from the bottom of the car to the top of the car. And we're going to call the height of the car H, okay? The height of the car is important here, capital H. According to observer B, this is how, well, I just don't want you peddling some false maths to the other students. It's okay. I'm giving you a break, but just change it to plus, okay? The laser is going to fire from the bottom of the car. It's going to travel in a straight line. So let me use my ruler for this. From the bottom of the car to the top of the car, where it's going to strike a detector and be recorded by both observers, but especially by observer B, okay? Now, if the car is traveling at a very uniform velocity, according to observer B, this experiment will be identical to an experiment in which the train car is at rest, sitting in the train station. The laser will fire from the bottom of the car up to the top of the car, and it will be triggered. So, according to observer B, so we're going to say B, what happens for the path of the laser? The laser is going to travel the height of the car, height H. It's going to travel it at the speed of light, and it's going to take some time to travel from the bottom of the car to the top of the car. This will be the start, and when it hits, it will be the end. Now, imagine the same experiment as observed by observer A. And here, if you want to talk about artificers here, imagine that I have one of those one-way mirrors like they have in the supermarkets to catch shoplifters. And imagine I install the one-way mirror in such a way that A can observe into the car, so he's aware of the experiment, but B cannot look out of the car, so he cannot tell that he's in motion. According to A, it's going to take time for the laser to go from the bottom of the car to the top of the car. And during that time, the cart will have rolled forward by some distance. What is the distance the cart will have rolled forward by? Well, let's track it relative to the laser. The cart will have rolled forward from here to here, and it will have traveled a distance, which I'll call capital D. Okay? During that time, this will be the start of the experiment, and the laser will hit the cart here at the end of the experiment. This is the time interval. And A will not see the laser travel in necessarily a vertical line, but A instead is going to see the laser travel along a diagonal. A diagonal where it starts here and ends there. This is the path of the laser according to observer A. Does everyone I need to make sure I didn't lose, well, I need to make sure I lose as little people as possible. Does everyone or does someone understand why this is the path of the laser as seen relative to A and not B? Can someone out there explain to me why A sees the laser take this path while B sees the laser take this path? Someone just regurgitate that for me so that I know that there's at least one person who understands me.
Because it travels so fast?
Well, it's traveling so fast, but the car is traveling so fast. It's not about the speed. It's about the fact that A sees the car in motion and B doesn't, right?
Yeah.
Like, for instance, if B was actually at rest, if B was not moving, both A and B would agree that the laser just went from the bottom of the car to the top of the car, correct? Both observers would see the same thing. The fact that A can see B moving means A sees the laser traveling forward in this direction as well as up. That's why it travels along a diagonal. Is the length of the laser beam that B sees the same as the length of the laser beam travel that A sees? And yet, according to Einstein's postulate, both observers need to measure the same velocity of the laser. So let's walk through this together nice and carefully. According to A, the path of the laser is going to look like this. Now, I'm going to call that triangular hypotenuse, just because I don't know what else to call it for the moment. I'm going to call it S, okay? The path of the laser taken by A is not the height of the car H. It's instead S. And according to Einstein, the velocity of the cart will not contribute to the speed of the laser. Both observers need to measure the same speed of light times the time. Now, you guys all agreed to me, correct, that S is longer than H, correct? But you also agree with Einstein that the speed of light must be constant, correct? I mean, that's what Einstein said. It's a postulate. If Einstein's correct that these are both the same speed, but these are different numbers, then time is no longer universal for both observers, and the different observers will measure different times for the same experiment. There is now no longer one time. There is the time according to observer A, T sub A, and there is the time for the experiment measured by observer B, T sub B. The two observers measure different times for the same experiment. My goal now is to attempt to connect these two and come up with a formula that relates A's time to B's time. And I'm going to do this here by using the velocity of the cart. The distance traveled during the experiment is the velocity of the cart times somebody's time. Let's see if anyone's been following me here. Whose time is measuring the distance traveled by the cart? TA or TB? Take a guess.
TA.
Very good. Was that you, Kaitlyn?
Yeah,
How did you know it was TA?
because B doesn't know that he's moving.
Very good. That's exactly what I wanted to hear. I'm very impressed. Excellent. That's TA. Now, I'm going to construct a big-ass Pythagorean theorem here. And the Pythagorean theorem is going to look like this. S squared equals D squared plus H squared. And then I'm going to substitute in all of these things with time. In for S squared, I'm going to put C times T. Okay. I'm going to need some friendly, non-threatening colors so that I can do this faster than average. C times TA squared. So that's what I substituted in for S. That's equal to D, which is V times TA squared. Plus, I'm going to substitute in for H, CTB squared. So basically, I took this, this, and this, and I substituted them in so that I have an expression that involves only TA, TB, the speed of light, and the velocity of the cart. And now I'm going to do a whole bunch of very fast algebra that nobody's going to care about. The first thing I do is I distribute the square to all of the parts. So I get C squared TA squared equals V squared TA squared plus C squared TB squared. Then I divide each term in the equation by C squared. This gives me TA squared equals V squared over C squared TA squared plus TB squared. So what I was doing there, so that you guys can understand, is I was just trying to get the velocities in the same term and just kind of clean this up a little bit. Now I'm going to subtract this side from that side. And oh my gosh, I'm already at 104. Anyways, I got a better idea. Eventually, algebra, you come up with our final equation. I'm just going to write it up here. The equation for time dilation. I didn't realize how out of the class I was going here. So the final equation looks like this. Let's see. TA is equal to TB divided by the square root of 1 minus the velocity of the cart over the speed of light squared. Please be careful to write that exactly the same way that I do. Okay. That took just a little more time than I had to work with. So here's what we'll do. Normally I would do a sample problem with that, and I'm just gonna, this is why today's lab, we needed more time, and I already knew that. Today's lab, we are gonna explore the consequences of this equation, and we're just gonna do some calculations with it, okay? That's the plan. So why don't you guys take a pause there? Take a 15-minute break or so. And when we come back, our lab today will be working with this equation, okay? See you then. Okay, everyone. Oh, actually, I owe you another 5 minutes. Let's pause. Okay, everyone. Why don't we get to it? Hello. Rocking that Baby Yoda. I just watched some Mandalorian the other day. Baby Yoda's still cute.
Guess what I didn't watch? Mandalorian.
Hey, don't spoil it. I haven't watched it yet.
Yeah, it's okay. I mean, Baby Yoda's great. But you should, just because, you know, when you see Baby Yoda, your heart will melt. Not a Star Wars gal, I guess, huh? How's little kittens doing, Emily? Oh, look at that little guy. That guy is freaking adorable. Have you named them?
My sister is still deciding on what to name hers, but I named mine Cricket.
Nice. And do they get along with those ferrets? They like don't try to eat each other or anything?
Yeah, they actually get along pretty well. I'm hoping they'll be able to play with each other once they're a little bit older too.
That's so cool. Wow. Kittens are nonstop entertainment. That's what we all need to get us through the second quarantine. We're gonna need kittens and wine.
I think actually shutting shit down again. I was so confused about that.
They probably should, Kaitlyn, because here's the deal. If you look at, like, if you go on the Washington Post and look at the cases for the United States, it's like 3 times as high as it was when we were in the middle of the hardest quarantine doing jigsaw puzzles and growing green onions. Like, it's gotten so hot. It's so scary to look at those numbers. Obviously, like, people are hurting, and if we shut everything down, then all these businesses aren't going to survive, and that's terrible too. I don't know exactly how I feel about it, but I know this. I'm really grateful that spring 2021 is going to be online, because I feel like we've all kind of adapted to this as well as we can, and this is acceptable. I think we still learn. And I know that when I was in school, like during the semester, I was in so close contact with people that I would get sick like every fall and every spring. It would just, I'd touch someone's pencil and eat a sandwich, you know? So I think having the schools closed is a good thing, because schools, just so many young people smushed together. It's tough. I don't know. I imagine, yeah, you know, it's people die from this stuff, so it's serious. Anyways, I don't want to waste your time. We'll find out, Kaitlyn, but I suspect they're going to try to bring things back a little bit. You might want to get your stock up on jigsaw puzzles or something. I want to do a couple of small things today, nothing super big. I want us to try a couple of calculations, and I want to show you a kind of sample problem that I'll probably give you on the exam. Now, this kind of took a while to do. Basically, I just derived the formula for time dilation. The first thing that we want to do is sort of do a sample problem with it, and you can include this as part of your lab. So, you know, on your lab, I'm going to erase this stuff here. All you'll need is a pencil and a paper and your calculator, maybe a ruler. So, you know, have your name. I'm going to do the lab here on the board, I guess, so I don't have to use my cell phone. This is lab number 10. And it's basically on something called the twin paradox, but we're going to get to that in a second. Don't forget to put AS1020 and whatever your section is, okay? Okay, the first thing that we're going to do is we're just going to do a sample problem in time dilation. And we're going to consider the experiment that we did at the end of our lecture, where there is an observer A who's standing on a platform, and there's an observer B who's inside of a train car firing a laser from the bottom to the top. And this train car is going to be rolling forward with a velocity, I think I said, of 80% of the speed of light. Oftentimes in relativity, we measure velocities not in meters per second or in kilometers per second, but in some percentage of the speed of light. So 0.8 c is a valid speed. Let's say, suppose firing a laser from the bottom to the top of a car is observed by observer B to take 2 seconds, okay? That's the time it takes for the laser to go from the bottom to the top of the car. We want to ask the question, how long will, and I'm going to use a charged set of vocabulary here. Instead of calling it the experiment, I'm going to say, how long will the event, I want you to underline that because that is a charged phrase. How long will the event take according to A? So to solve this problem, we're going to want to use our time dilation formula. Okay. Let's set it up as follows. We are not going to convert velocities to meters per second or kilometers per second. We are going to write TA is equal to, TB is 2 seconds, divided by the square root of 1 minus, now in for the velocity, I'm going to substitute 0.8. I'm going to use red for the speed of light in an attempt to show you guys how this works. So let me use colors to help you see the algebra here. This is 80% the speed of light. So I substitute in 80% the speed of light for the velocity, and that will be divided by the speed of light. And all of that must be squared. So start by writing this down. I want you guys to notice that the speed of light appears top and bottom here. So we can cancel it out. And this just becomes two seconds divided by the square root of 1 minus 0.8 squared. Okay. Now, I think you guys should try punching this in on your own. I bet nobody gets it right because punching this into the calculator, you have to be very careful about your order of operations. But I suspect you guys will learn more if you try it once on your own and fail, rather than me showing you how to do it the first time. So could you guys just start by trying to do that on your own, and let's just see if anybody can get it. Just want to see what I'm working with here.
I got 3.3 repeating.
Christopher, you did it right. Show me your calculator. Yeah, you've got a, one of those TI-85s is actually easier because you can take care of order of operations. I want to see if someone who's rocking the Casio can do it.
Well, it's a Casio 115.
Yeah, that's a line entry calculator instead of an instantaneous one. Hold it up. Okay. It's close, but it's not correct. Kaitlyn and Stacy. Okay. Guys, I'm going to walk us through this, clear it out, okay? Let me tell you my strategy for dealing with this. I want to talk to you about it, and then I want you to watch me do it. But I need you to understand my path here. I am going to first do 1 minus 0.8 squared, and I'm going to hit equals. Then I'm going to square root that. Wait a minute. Don't start doing it, Kaitlyn. Just listen for a second, okay? Sorry, I can't hear you.
That's what I did the first time.
Real, but hold on. Just hear me out. We're going to do 1 minus 0.8 squared. We're going to hit equals. Then we're going to square root that. Then I'm going to hit the reciprocal key to flip it to the bottom, and then I'm going to multiply it by 2. That is the most elegant way to do this. Okay, so follow along with me. Just learn my methods here. 1 minus 0.8 square, and now equals. You should see that so far. Now, shift square root. You should see 60%. Now we're going to flip it to the bottom because that's where it should be by doing shift 1 over x. That's what you should have. And now we will multiply by 2 seconds. And you get 3.3 forever. Did it work? Stacy, are you saying it didn't? All right, that's good, Kate. Emily? Stacy, what's going on?
I was watching you, but I wrote it down. I took notes, so I'm good. Thank you.
No. I don't.
All right, then give me 1 second.
Okay. There's saying you're good does not mean you're good. When I see this, then you're good.
Okay.
Just trust me. I've learned this stuff the hard way. Wonderful. You are good.
Thank you.
We need to analyze this, class. Okay. The meaning of time dilation can be expressed in the following phrase. The phrase, there's little mantras that go along with the equations of relativity. And the phrase is moving clocks run slow. Let's analyze our 2 times. A's time was 3.3 seconds. B's time was 2 seconds. Class, which clock ran slow? Which clock is the slow clock? First of all, who's moving?
B is.
Kaitlyn says B is moving. Whose clock is slow?
Is it also B?
Yes. Why is 2 seconds slower than 3 seconds? I just need to make sure that you can follow that logic.
Because it's moving, I think.
Okay, yes. B is, you can say for now I will let you say that B is moving, but you're missing the point. Why is a 2-second measurement slower than 3 seconds? We need to get confused, and then we need to get unconfused. Let's start by getting confused. Which time seems slower to you? 3.3 seconds or 2 seconds?
2 seconds.
Good, but now explain why. Why is 2 seconds a slower time?
Like, the action that happened, time A measured it in one way, but time B measured it in a different rate. So time A got 3.3 seconds, so that clock was running quicker. Time B got 2 seconds, so it was running slower.
I think you actually did okay, Christopher. It's about the rate at which the needle on the clock is running. Like, what is slow? I need a prop here. Here's my prop. When we say slow, we're talking about the rate at which this needle hand is running on a clock, okay? Do you see this? See, the problem is people get confused because if you are runners in a race, someone who ran a race in 2 seconds would be considered faster than someone who ran a race in 3 seconds, right? But that's if you're measuring the speed of your runner. Here we're measuring the rate at which time is flowing, like on my clock. So Christopher is correct that if we have 2 clocks, if B's clock measuring the event elapses 2 seconds, and A's clock elapses 3.3 seconds, then for the same event, the needle on A's clock was running fast and the needle on B's clock was running slow. Did everyone see that? Okay. Okay, here's the problem. In our setup, A was the observer who was at rest in the train station. B was the observer who, by Kaitlyn's own admission, was moving. And yet, Kaitlyn, did we not argue that according to the principle of relativity, any observer in an inertial reference frame could always argue that they are at rest and that the other observer, the observer on the train station, is the one in motion? Isn't that possible according to the principle of relativity?
Yes.
See, Kaitlyn, if I were B, I wouldn't think that I was the moving clock. I would think I was the rest clock. And now I'm going to ask you a really weird question, and I want you to think carefully about it. You're probably going to stumble on it, but that's sort of the point. Let me write this question out in hopes that you will remember it. What if observer B in the train car were to cut a little hole into the car and use a telescope and try to observe A's clock during the experiment? I could then ask you a question: how much time elapsed in A's frame according to observer B? Does anyone think they could answer that question?
I want to say like it would still be 2 seconds. They just think the clock is going fast.
No. It would not be 2 seconds, and this is why, Christopher. Because B now believes that he is at rest, and the time that's elapsed in his frame is 2 seconds. Meanwhile, he sees A, in a sense, traveling past him in a spaceship called Earth at a velocity of 80% the speed of light. If B measures an event in his frame that is 2 seconds, A's frame is a moving frame with respect to his, and he must see A's clock, the moving clock, run slow relative to his. 3 seconds is not slow. 3 seconds is fast by your own admission. Can you tell me what the new time will be? In a sense, we've rearranged the configuration of A and B. We have now made B the observer who believes they are at rest, and we've set their time to 2 seconds, and A now becomes the moving frame moving past them. In essence, the equation now looks very different. It now looks like TB is equal to TA over the square root of 1 minus V over C squared. But TB is now equal to 2 seconds. If we solve for TA's time relative to B, we will get the square root of 1 minus 0.8 squared times 2 seconds. Calculate that for me.
$1.2
seconds. Christopher, there are now 3 clocks. 3 clocks. There
Did
is
I mention that I hate this?
there is A's measurement of time. A measured the laser fire to take 3 seconds. B measured the laser fire to take 2 seconds. But meanwhile, B, looking back out onto A's platform, sees only 1 second having elapsed because A is a moving observer relative to him. None of the observers agree on time, and each observer thinks the other observer experienced a shorter time interval. What if it... Well, Einstein kind of already did that for you. He already destroyed it. I'd like to point out that A and B have the same units. So if instead of it was 3 seconds, if it was 3 years, the answer would be 2 years on the other side. It wouldn't matter. Time runs slower in a moving reference frame relative to a stationary observer. No 2 observers will agree on the same length of time if they are moving quickly with respect to one another. Now that you've understood the calculation, it's time for us to do one of the wiggiest paradoxes in all of relativity. It's called the twin paradox. In the twin paradox, we have twin brothers who at the age of 25 years old invent an interstellar spaceship company. Let's put them over here on planet Earth. One brother takes the role of the businessman. He's got a briefcase and he does some taxes. We'll call that brother A. And he's the one who runs and crunches the numbers for the spaceship company. Brother B will be the spaceship pilot. He's the one who gets to be inside the spaceship and travel to a nearby star system, say Alpha Centauri. And he's going to travel at a velocity of, let's jack up the speed a little bit. Their spaceship has a top speed of 90% the speed of light. By the way, I don't know if you guys know, but last night, the Sunday and Monday, they sent another Dragon space capsule to the International Space Station. They sent 4 astronauts there. Did you see that? It's pretty cool. And it docked successfully. And it's, man, those space suits and that touchscreen stuff, it looks so cool and modern. It's nice to be a part of this. There's so much bad news these days. It's cool to see something exciting and happy take place. So Brother B is going to take the spaceship trip to the nearby star system of Alpha Centauri. And I believe, Christopher, you know the distance to Alpha Centauri, don't you?
I think it was 4 light years.
4.4 light years to be exact.
Yeah, round down.
Okay, that's fine. Our goal is to ask ourselves, how long will the trip, let's talk about a one-way trip for starters. A one-way trip for observer A versus observer B. We want to ask, how long will the trip take according to first A and then B? So we have 2 questions here. Okay, let's start with observer A. For observer A, I'd like to point out there's honestly no relativity involved. And that's because A is basically just watching the spaceship travel at a very rapid velocity from Earth to Alpha Centauri. All we really need to use here is distance equals rate times time. The distance traveled according to A is the velocity of the ship times the time according to A. The distance that A measures to Alpha Centauri is 4.4 light years. The velocity of the ship is 90% the speed of light. And therefore, we can solve for A's time by doing 4.4 divided by 0.9c. Class, what units should we substitute in for C?
Kilometers per second.
Kaitlyn, I see 2 problems with that. You could do that, but if I use C as 300,000 kilometers per second, won't I then have to convert my light years to kilometers as well?
Yeah,
And what will the units of time that I get come out in the end?
I don't know.
Yes, you do. Kilometers divided by kilometers per second will give you what units? Wait, Kaitlyn, come back to me here. It's got to be a unit of time, right?
Yeah, yeah, I guess.
So if it's kilometers over kilometers per second.
Oh, would it be seconds?
Right. But is that the best unit of time to use for a trip from Earth to Alpha Centauri? What would you rather have the units come out as?
Years.
Years. So I've got a suggestion. Instead of doing all that work, instead of using, let me just go up here for a second. Instead of using C as 300,000 kilometers per second, we can make our lives really, really easy, simple here. If we only knew the speed of light in light years per year. Is there anyone out there in the studio audience who maybe could guess the speed of light in light years per year? Chris?
1.
That's right. Because by definition of a light year, it's the distance light travels in 1 year. So Kaitlyn, although our first instinct was to use 2 kilometers per second, if we use light years per year, then we kind of don't have to do anything, which is way better. And our answer comes out in years. That's a little trick that you probably would like to know about on the exam, but you would probably never think about on the exam. So please remember that trick. Okay. Guys, calculate the time that A will see his brother take as he travels on a one-way journey to Alpha Centauri. Two sig figs.
4.9 years.
So 4.9 years, so pretty close to 5 years. That's kind of cool, actually. That tells me if I could build a spaceship that traveled at 90% the speed of light, I could get to the nearest star system in 5 years. Now, that's a long time, but humans might be able to put up with that. Maybe, if you gave them a lot of puzzles. Okay. Now let's try the other one. Observer B is going to experience, obviously, some time dilation. Because according to, or freeze them, yeah. I don't know how well that would work, but I don't know if I'd want to be frozen for 5 years. B is a moving clock relative to A. So A is going to observe B's time running slow. Can you guys tell me how to solve for how long the trip takes according to B? What do I do? Let's pretend this is the test. Your next question is, how long does the trip take according to B? What are you going to do?
So you would do TA over
Yes.
1 minus V over C squared, square root.
Hold on. Read that out to me again. TA equals what?
TA equals TA equals 4.9 years.
No. I want it algebraically first to make sure we have the right formula. Sorry, buddy. Give me the
TA equal, I thought we were solving for TB.
Well, we will eventually. Oh, I see. Okay, yeah. But I just wanted to point out, because we got confused last time, that we just want to use the standard formula for time dilation. 1 minus V over C squared, right?
Yeah.
And then you were trying to rearrange it for TB. Is that what you were doing, Kaitlyn?
Yeah.
Great. So tell me what that would look like then.
TB equals TA over.
No, you're taking this factor or this term and you're multiplying it up there, right?
Oh, okay, I gotcha. So
it's TA times the square root. Do you agree with that?
Yes.
Okay. So in other words, TB will be 4.9 years. Sorry, it's getting a little tiny here. Times the square root of 1 minus 0.9 squared. I better write that up top because that's getting a little messy. Do you sort of agree with that? Sure, why not? All right. Let me write that up here so we can see it a little cleaner. TB is 4.9 years times 1 minus 0.9 squared. I'd like you guys to punch that in for me.
I got 2.1 years.
Me too.
Cool. Approximately how old will A be when his brother gets to Alpha Centauri? Roughly speaking, how old will brother A be?
$29.9.
30 years old, right?
Yeah.
How old is brother B going to be?
7.
27. They're not the same age anymore, are they? The brothers are no longer the same age. Now, you might ask me, what will it feel like if you're brother B? It won't feel like time is running slow. When you're in the spaceship, you don't feel like you're in slow motion. You feel like time is normal because you're at rest with respect to yourself and your heartbeat has a normal rate with respect to yourself. What you will think is that everybody else's time is all effed up because, and here's the real paradox, according to B constitutes an inertial reference frame. B is traveling at a constant velocity. Therefore, B could successfully argue that he is at rest and that it is planet Earth and Alpha Centauri that's flying past him at 90% the speed of light while he's just chilling. Okay, final question. This is the essence of the twin paradox. I need to erase this because I'm out of space. Can I erase this? So we saw that TA takes about 5 years. TB takes 2.1 years. Well, let's use the 2 sig figs because of the next question. Okay, here's my final question. How long will, actually, let me ask it in this way. How much time has elapsed on A's clock according to B during these 2.1 years? How much time will B think has elapsed on A's clock according to B during these 2.1 years? Can anyone calculate that without my help because they understood the previous problem? Can anyone do that without my help? I can show you how, but it would be cooler if you guys understood enough to do it.
I think I get it.
Okay, so
it's
what's the number?
So it'd be, well, hold on. Give me a second.
Sure. Just do what we did before. Feel free to have one of those trolls participate in the background too. No wonder no one's turning in their work. I lost like more than 50% of the class.
Would it be 4.8?
Nope.
Wait, what did Chris say?
Pardon?
What did he say? I'm sorry.
He said 4.8.
Okay, I got 0.9. Well, 0.9.
Whoa! Kaitlyn, you are the master of relativity calculations. 0.9.
I don't even know how.
I'll tell you how she did it. Okay. Just like we did last time, we are now rearranging the moving observer and the rest observer. So B is now going to consider themselves to be at rest and A to be in motion. Right?
That's not the formula that I used.
But then you solve for TA. It is the formula used. If you solve for TA, TA is TB, 2.1 years, times the square root of 1 minus 0.9 squared. Is that not the formula you used?
I wrote it down backwards, but yeah, that is what I used.
See, then that is this formula because I've swapped the positions of TB and TA.
Yeah, I didn't realize what you were doing at first. Sorry.
That's okay. And if you do this, according to B, only roughly 1 year has elapsed on Earth during his trip. How old will B think his brother is when he gets to Alpha Centauri?
About a year older.
26 years old. Each brother thinks the other brother is the younger brother. Each brother thinks less time has elapsed in his brother's frame than in his own frame. So of course, the whole nature of the paradox is what happens when B turns around and comes back? According to A, that'll take 10 years. And A will think it takes 35, he'll be 35. According to B, it'll take 4 years. He thinks he's 29, but B will think only 2 years has elapsed in his brother's frame, and he'll think his brother is 27. The essence of the twin paradox is this. When the brothers get back, which brother is going to be the younger brother? This is a paradox in that it has no real solution. It's just messed up. Now, people do try to propose solutions. One of them is if brother B turns around and comes back, he will have to first decelerate, slow his ship down, and then he'll have to reaccelerate in the other direction. That will no longer be an inertial reference frame. Thus, B will constitute a moving frame, and B will actually be the brother in motion. So probably what will actually happen is brother A will be 35 years old when B gets back, and brother B will only be 4 years older, or 29 years old. They were once twins. Now there's a 6-year difference when they return. Pretty cool stuff.
Did I mention that I hate this?
What's to hate about this?
Why?
It's wonderful. It's fun. And you can come to terms with it.
It pisses me off that they should be the same age and they're not.
Do you guys know they did a famous experiment in the 1960s that showed this actually happens? It's known in physics as the Hafili Keating experiment. And what they did is they got these atomic cesium clocks. So the idea is if you move slower than the speed of light, there's still a measurable time difference, but it's like a millionth or a billionth of a second. So they got these atomic cesium clocks that could measure time down to a small fraction of a second. They rented out a jumbo jet and they put one clock on the jumbo jet or this high-speed commercial airline, and the other one they kept at the airport, and they flew around the world 2 or 3 times. And when they landed the plane, the clocks had a different discrepancy in time that was exactly calculatable by special relativity. One of the coolest things about this is the famous iconic photograph of the experiment that appeared in Life magazine. And as a parting shot, I'll share this with you. It's called the Hafili Keating experiment. And just because they were having a good time with it, you know, this is 1960s, the era of Mad Men and all that stuff. And this is the iconic photograph. So here we have, it's low resolution, but we have the 2 scientists, right? Sitting there with Mr. Clock, and they're all dressed up like, you know, 1960s in their suits. They've got the stewardess there, and they're probably drinking highballs or whatever, because they're going to be on the plane for like 5-10 hours. And they took this iconic photograph for the memory books, and the stewardess is kind of coyly looking at her watch, which is a really funny double entendre, right? Because she's making a joke. The first part of the joke is, okay, we're doing an experiment about time. The second part of the joke is, geez, I'm really fucking bored because this is a really boring experiment. We're sitting on the plane for all these hours. And they're obviously all in on the joke and posing for this thing. So just a totally clever moment there in science history where they had a little bit of fun with it. In any case, you can hate it if you want, but unfortunately, the Hafili Keating experiment shows us that this time dilation does happen. You've never noticed it in your travels to the grocery store because you don't travel at 90% the speed of light. But if you did travel above 20% the speed of light, these things would become more apparent. Now, this is your first gateway into relativity. On Thursday, you will learn more about it, and eventually we'll have to use this to understand the death of stars. But for now, you've done more than your fair share of work for the day. Now, you guys are all going to turn in the work that we did here, correct, as your lab? That's what I need you to do. I also need you to study this problem because I'm going to ask you this problem on the final exam. Now, you already did pretty good your first time around, so I have faith in you, okay? All right. How'd we do on time anyways? It's a little later than usual, 2:19, but that's not so bad. Okay, does anyone need or anything else from me or have any other questions before we stop? No? Okay. Well, thanks very much for playing. I'm going to kill the recording.